So we've been looking at low rank approximations for matrices. This is sort of the final talk in that series, and we're going to be talking about matrix sketching. And this does sort of the same kind of things. It creates a smaller approximation for a given matrix, but it does it in a streaming fashion. So remember how when we considered the UV decomposition, we talked about gradient descent first, and then we switched over to stochastic gradient descent so that we are accessing the matrix only once. And in many cases, because the matrix is too large even to fit into distributed memory, or if the data itself is coming in a streaming fashion, you might want to have these kind of algorithms. It's a very clever algorithm, it's very nice, and I've tried to keep the math right till the end of the class, so hopefully all of you should follow this. It's simple enough, so you should follow it, and I would ask questions if you get stuck anywhere, because I think it's important you understand it. It's simple enough that all of you should be able to understand 99% of this. So again, last time we talked about SVD and randomized SVD, and today we are extending that to matrix sketching. Couple of logistical issues. I am not here, and this is a good break for you guys. I'm not here the next week, and I'm not here on Wednesday either. So the next lecture on Wednesday is going to be on the security aspects of big data. So when we talk about big data being everywhere, Facebook and Google collecting information, there's a lot of privacy and security related aspects. There are also aspects related. You might have heard recently that different vendors give you different prices depending on who you are. So there is a sort of a discrimination which goes on as well. So there are several aspects, and Professor Denning is going to be talking about that. She'll give a guest lecture next time. Next week on Monday, the TA is going to give you a general tutorial and an introduction to Spark. A lot of you asked for this, so I thought this is a good time when I'm not here. She can go over a full tutorial explaining this to you, and she's going to start off with Hadoop, and then she's going to talk about both Scala as well as Spark, which are nice frameworks. The next assignment is going to be a little bit different for a couple of reasons. All of you guys, at least this is the feeling I got, that even though I asked you guys to work as a team, you were sort of dividing up one problem to one person and the second problem to the other person. I really want you guys to work. So there's only one problem in the next one. I'm giving you a flexibility of choosing the programming model. You can use MPI, Hadoop, or Spark. I would suggest, especially if you're happy with the TA covering Spark next time, that you opt for Spark. It's going to do you a lot of good, and many of these are probably ideally suited for either MPI or Spark. Baby Spark, better than the others. I want you to implement one of these low rank approximations. You have the flexibility to choose. So it's going to be either you implement the UV decomposition using stochastic gradient descent, randomized SVD, or matrix sketching that we are going to cover today. So I want you to think about it. I'm hoping that not all of you just choose one of them because that appears to be the easiest. From your own experience, your initial intuitions have probably been wrong on how easy or how difficult something is. So try to think about which approach you want to do, and I want you to have a justification for why you picked it. So you have the full flexibility. This would also be a good time. I'm not here. The next week is going to be a little bit less busy for you guys. You should start thinking about your project and linking this up. Making both of these choices somewhat dependent on your project might be a good idea. So think about it. I will have access to email, so please send me emails. Whenever you have any issues, send me an email, I will reply. So think about your project and think about how you're going to implement it and whether any of these decisions help you that direction.
How is Spark? We understood MPI and Hadoop. Can you tell us how Spark is different? What is it trying to achieve?
So Spark has been built up. It's sort of, the easiest way I would say is that people who are traditionally doing MPI suddenly realizing that Hadoop doesn't work as well, and they're trying to go for a middle ground.
Okay.
So loosely put, it does a lot. So Hadoop does everything off the file system.
Yeah.
Spark tries to retain some information in memory across jobs. It has access to HDFS, so you will run it on the same machine. You will run it on top of Hadoop, but the programming model itself will give you flexibility. And there are a few other variations. So it's going to appear somewhere in between Hadoop and MPI.
So in Hadoop, after every map and reduce, right now we are writing the files.
Yes. So the classic situation where Spark wins over Hadoop is our iterative methods. Because if you have something simple where I have a small amount of information to be retained for the next iteration, I can keep it in memory. You don't have to go back and forth to the file system.
Write to file system between map and reduce tasks internally?
Yes, it does. And that's why. The needs were different, and that's why Hadoop was built that way. Okay. So Spark, again, depending on whom you ask, some people will say this is going back in time effectively because this is how the earlier systems used to work. Okay. So hold on a bit, I'll answer more questions. I really want to get through this lecture because it is a very clever algorithm and it is fairly simple, okay? So just a quick bit of motivation here. We've looked at a lot of problems where data is usually represented as a matrix, right? For a lot of the big data applications, this matrix is too big, and it's sort of motivated us to do things in parallel, whether MPI or Hadoop or whatever. Of course, you have to consider the case where it's the matrix itself. So think in terms of doing a matrix vector product just for the time being. If the matrix is so big that I cannot even store it in distributed memory, right? So we talked about, you guys implemented matrix multiplication for page rank unit matrix vector. We were still dividing up the matrix into blocks, but we still assumed that all the map tasks would be able to store this matrix, whether it's a sparse or a dense matrix, that it can sit in memory. But you can imagine several cases. Let's say that you are Google and you wanted to run on the entire, do a page rank on the entire web internet right now on something like app, which means that we won't have enough memory to have that matrix loaded in the distributed RAM. You can have it on disk because it's probably a few terabytes of data, but you don't have that much RAM, right? So you have to consider the situation where it's too large, which means that we want to process these in a streaming fashion, which is that you're reading it from disk and computing your approximation. Remember, specifically for randomized SVD, the one that we did last time, we were using projections. We were using matrix vector products. We were taking k random vectors and performing a matrix vector product there. So it was A times the random k random vectors.
So when you say it doesn't fit in the distributed memory system, it's still on the disk. Right now, that's how we are doing it. We have it on the disk, and keys are getting loaded up based on which nodes touches which keys, right?
Yes.
Would they need? Why would it? So in some sense, all of that need not be on.
No. So the way it works is, so let's say that you wanted to do randomized SVD. Okay. What are you doing? You're doing A times another matrix, but let's think of it as k vectors, right? That's how we did it. Which means that you'll have to do k matrix vector product. Okay. Yeah. Now the matrix vector product could be done however you implement it in Hadoop. If you had to do k now, you're going to be reading this matrix k times, or basically the general assumption is going to be that you're going to have that in memory. Yes. Right? You're still loading. So the map tasks are loading the values.
The reduce task needs the reduce task only goes and picks all the keys which it wants. Right? It shouldn't pick anything which it doesn't want.
Yeah, but across all the reduce tasks, you still need access to all the non-zero values of the matrix.
That reduce task is out of memory.
So basically, if I cannot have my memory, the matrix A in memory, at least the non-zero, that's what I'm saying. Ignore this, whether it's a sparse or dense matrix. You're still having that much in memory at some point, right? So you still have a bottleneck. So one way would be, so what we are trying to do is that we want to, in some sense, optimize. So you could do it. Using Hadoop, you can do it, but then you're repeatedly doing this. You're accessing that matrix multiple times. It's not that you can't do it, it's an efficiency of what you're doing. So sketching takes a slightly different approach. It says that I have this matrix, I'm going to read it in, but I'm going to read it up only once, and I'm going to access a small portion of this data. It's accessing, in this particular case, column by column, but it's accessing each column once, and that's it. It loads a part of it, it does something, gets rid of it, moves on. So the algorithm that we're going to talk about today could even be done in a sequential case. So it's the same idea that you would use if you had a single machine, let's say with infinite disk space. I'm reading it in, I could still do it as long as I can fit one column in memory, right? And correspondingly, you can expand it into a parallel scenario as well. Okay, so it's pretty similar, but the motivations are different, and it's important that you understand it. Okay, like I said, it's streaming, so it also fits in well with a case where data is coming in. So if you consider your matrix, where we typically talked about sort of users and their preferences or items and how they rate it, maybe you're getting data coming in either item by item or user by user, in which case you're bringing it in a one-by-one fashion. There's an inherent order in which the data is coming in, and you don't want to store it. So if you go back now to the previous argument, you would first wait for all the data to come so that I can have the matrix A on disk or in memory, wherever, and then I can go ahead and start generating the approximation. So at least for these two scenarios, this is a far superior solution. Is it clear? Do you understand the differences? So let's sort of just generally look at what it is that we're doing. So it's the same logic that we had. There are a few variations. Basically, we want to compute an approximation which is smaller than our given matrix, such that it approximates it, which means that it's sort of good enough. It's the same thing as what we talked about. It's an approximation. It's not exact, but it gets most of the information is retained. So it's losing some information, but hopefully that's at the lower end of the spectrum, so things that don't matter as much. And sketching tries to basically prove similarity in terms of two senses. One is with the matrix itself, subject to some norm, or in terms of the covariance matrix itself. So for a lot of the statistical operations, for a lot of machine learning codes, it's the covariance matrix that's important. So you want to make sure that it's also similar in the covariance matrix sense. And when we look at it, you'll realize that from SVD, if we looked at it, they're going to end up being somewhat similar as well. And again, there is the issue of dimensionality reduction. Maybe we want to do matrix multiplication at some point, but having the approximation is better than doing it, especially if you're doing any operation repeatedly with this matrix. Spending some time and effort to first generate this sort of a smaller approximation helps you. Yes? I'm going to get to that. That's what the talk is about. I'm just motivating you right now. So,
what is this? Maybe you covered it, what the covariance basically indicates.
So the covariance is that, so if you have a bunch of variables, you're looking at how they're related. So in a matrix form, it's just telling you what is the relationship between how similar one entry is to, or knowledge about one of these entries tells you about the other one.
So like you're saying you're approximating A to B, whatever.
Yes. So B is the approximation, A is the original matrix, the full matrix.
Yeah.
So when we generate an approximation to something, you want to define in terms of
There should be some equivalence at least.
exactly in what form is it equivalent. So the first version is where you say that subject to some norm, the entries of the approximation B are going to be equivalent to A. Okay? They are of different sizes, so which means that I am defining some approximation which is going to some metric, some norm, where I can compare these two, right? We'll get to the specific comparisons in a minute. The other case is that because if we are interested in operations which work not on the matrix directly, but utilize the covariance of the matrix, which is in this case, in the standard sense, the covariance matrix is the matrix transpose, or the matrix transpose matrix, then I want that to be similar. So you could have situations where B and A are not exactly the same, but the covariance matrices are similar. In this particular case, when we generate the sketch, this particular algorithm is going to guarantee closeness in the matrix norm sense. In this, the typical sense would be the Frobenius norm or the induced norm, and as well as the covariance matrix itself. Okay?
And again, a basic question, like on a general idea, when you try to approximate a matrix of say n cross d dimension, so your intention is basically to reduce the number of rows in a matrix, or is it to reduce the attributes like the columns of a matrix?
So you are going to look at both cases. Just wait until the next slide. Typically what you're doing is that you're reducing the number of columns that you are retaining. Okay? But if you remember from the previous lecture, in the SVD sense, what you are doing is that you would typically project it on, you would basically remap it in some sort of an orthonormal basis and say that I'm only retaining a fewer number of bases. So this is reducing the overall dimensionality of your matrix or your data as such. So they are sort of related, but not always the same. So the algorithm that we are going to consider here is called frequent directions. It's by Ido Liberty, and it's a very recent paper. It's a well-written paper, so I'll put it online, and you should think in terms of, you should read it. So answering your specific question, right? We want to generate a matrix B here, right? And it's a flexible algorithm, so you can define what is the level of storage you want and how much data how good the approximation is going to be. So typically when we talk about approximation algorithms, we give it a parameter which we can adjust. So the more the number of columns we retain, the better the approximation, right? Intuitively that should make sense, that the less I get rid of, the better my approximation is. So in this case, we parameterize it saying that we are only going to retain L columns, okay? And let's say that we specify L in terms of 2 over epsilon, where epsilon is a measure of the error that we want. It's inversely proportional, which tells you that the smaller the error or the higher the tolerance that I want, the closer I want my approximation to be to the original matrix, the more the number of columns I would have to use, okay? So that's the storage. So we talked about a matrix which is too large to fit into memory. And now we want to say that we want to get an approximation which is smaller. If you say now that there is this massive billion by billion matrix, and I only want you to retain 10 columns, your approximation is obviously going to be inferior. It is possible that your original data was sparse enough and low dimension enough, or the matrix was low rank, that you would be able to do it, but in general, these are the bounds that you can specify. And typically what it's saying is that this is the kind of guarantees you can give. So this is in the L2 norm, the difference between the covariance matrices is bounded by the Frobenius norm of the square of the Frobenius norm of the input matrix scaled by this error factor, epsilon. Okay? We'll prove this. So just understand how we are trying to set up the problem. Yes?
What is the motivation for this error?
Sorry?
What was the motivation for the definition of this error?
So the motivation is that you want to have a control, right? You want to be able to control the...
I know you want to be able to control the
Yes.
whole point of approximation algorithm. What was the motivation of defining the error of this way?
The error this way is because of how the algorithm is. This is a proof for it. It's not that you're defining the error this way. No.
So what is the intuitive meaning of this? If I say AA, how much does this impact? How does this impact this? If I calculate the differences of variances,
Yes.
look at the norm,
Yes.
the Euclidean norm,
Yes.
if this has to be smaller than the epsilon of Frobenius norm.
Yeah, it's telling you how close the approximation is to the original matrix, right?
Yeah,
So
but you have two different norms. I have no idea how it is.
So the norms are going to look very similar. So in this case, the norms are it's actually coming from the trace. So the Frobenius norm here is going to be the trace of AA transpose in this particular case.
Trace
wait till the proof part. Understand the algorithm first, I'll get to the proof. Okay? Let me derive this, it will become much easier, clearer that way. So, from an intuitive perspective, the algorithm extends the idea of a frequent items algorithm. What it is doing is that, think of now not a matrix, but a stream of entries. So you're getting some values coming in. Maybe you're a router and you're looking at IP addresses which are accessing data. And you want to sort of figure out who accesses data most frequently. So you basically want to query at a given time and say that what are the most frequent items that are being accessed. And so you can think of designing a streaming algorithm to do this, right? How would you do this? If you were just having a stream of some set of values and you want to figure out what is the frequency which they occur. Let's say I'm the person in interest and I'm looking at the frequency with which you guys are showing up in class, right? So not all of you are showing up in all the classes, so I want to figure out how frequently you come. What am I doing? No, I'm just keeping a counter, right? I'm keeping a counter for each of you, and every time I see one of you in this class, I increment it, and at the end of it, I know who's shown up how many times. Correct? Now think of a case. Again, this is the motivation for what we're trying to do for the matrix. So extend the same thing. Say that I don't have enough memory, or I don't want to maintain a list of, say there are 40 students here, I don't want to maintain a list of 40 students. And I want to instead only save 10 students. Because at the end of the day, I'm only interested in the 10 students who attend most frequently, and they'll all get 10 extra credits at the end of the semester. Okay? So how would you do this? So the question now is that in a streaming fashion, without having full memory, can you do this? Which is sort of the same extension to the matrix case, but it's much easier if you consider now this one-dimensional case and stuff. So it's a vector of items which are showing up instead of a matrix. Okay? So the goal is to make, so you have some n items. In this case, they're different colors, and they're showing up. And I'm saying that, here are some D colors, and I'm retaining them. And what you basically are saying is that I want to count how many there are. And this is easy, right? This is the simple approach. So I have D counters. As every item keeps coming in, I keep incrementing their counters, and I always have a list of what I have. Okay? So it's the frequency in this case that is of interest. So the question, of course, is what if D is very large and I can't store it? Okay? We sort of did something along these lines when we were looking at clustering, but some of it will probably come back to you soon. So the idea is, and this algorithm is called frequent items. It's proposed by several people, but we're looking at a version by Mishra and Rees. And the general idea is, again, say that we're going to maintain a bunch of counters which are less than the total number of variables that we have. Let's call it L. This is going to be similar to the approximations that we were doing for the matrix. And so, again, intuitively, these are approximations. So we're not going to get exact frequencies for every item, but we get an approximation which is going to depend on how small or how large L is. Okay, so that's basically where your ratio is. So the general idea is that you maintain L counters with one extra constraint, that at least one of those counters is empty. Okay? So I have a bunch of counters. They are labeled as what, in this case, what color it is and how many times I've seen it before. And I have at least one empty. So as a new item shows up, right, you have two possibilities. This item is something for which you are maintaining a counter, in which case it's very simple. You simply add one to that counter, and you have updated your frequency list for that item. If you have not seen this item before, then you basically insert it into the empty slot that you have. Like I said, you have to guarantee that at least one empty column exists. Okay? So you're maintaining at least one empty counter, and so if you see a new item which is not there, you insert it there. Okay? Is that clear? Of course, now we have a problem, right? We have a problem that we don't have an empty slot, because if the next item comes out and it's a different color, then I don't know where to put it. So we need to sort of readjust this set of counters we have to empty out some of them. We need to figure out how to get rid of some of these. So let's assume that delta is the median counter value at some given time. So this is at some time we have received a bunch of items. Let's look at the median. In this case, it's an even number. Let's assume median is 1. You will subtract the median value from all the counters. Okay? So you basically erased away the least amount of information that you had. So whichever counters were sufficiently frequent will retain some information. You have scaled them down by whatever you got rid of, and now you have some empty slots.
I forget what the empty slots are.
They're just counters. So if you said that there were 10 colors to start off with, total.
Yeah, but I'm remembering which counter belongs to which color, right?
Yes.
Now I won't, if once there's zero, I won't remember.
There's nothing. These are blank slates right
So
now.
how do you delete that on what basis?
The median. So you look at the median value out here for all of them. I'm basically saying that I'm retaining half my information and I'm getting rid of half of them out here. Right? On the median value, so the ones which are most frequent will be retained, the least frequent are gotten rid of. Right? If you remember our clustering approach in time where we were trying to do arbitrary periods of time, we were sort of doing the same thing, except in that case we were clustering them together in a binary sense. Here you're discarding it completely, because our goal is not to maintain the full thing, but to only retain the most dominant frequencies. So you get rid of this, okay? And now you can continue doing this repeatedly. So as items come in, if you have an empty slot, put it in if it's there. If it's not there, you get rid of it. Okay? So the algorithm itself is fairly simple. Does everybody understand what's happening? Right? So for the frequency f prime, right? And you all should understand that by its basic definition, f prime for here I means a particular item, right? A frequency for a particular item. By definition is going to be less than or equal to f of I. Yes? Is that clear? Because every time a new item comes up, we are increasing f of I, right? We're adding 1 to it, but occasionally we are reducing some values from some of these things, which is what is in our f prime.
F prime is just a symbol notation, it's not differential.
It's not, right? So this is just our approximation here. So that's the frequency that is retained by our approximate solution here. Now, because we decrease each counter by delta t, the median, right? Here t is the time instant. At whatever time instant we decided to decrease it, f prime of I is greater than or equal to fi, right? The true frequency, minus summation over all t delta t. So because this is the total amount that you decrease. Now in some cases you might not participate in this reduction, so this is an upper bound, right? So this is going to be always greater than the actual frequency minus the total amount that you reduce at every single step. Is this clear? So can you see the slides? Okay. So what am I saying? So this expression is saying that I have f of I. This is the true frequency. So every item that I see, I am recording it, right? Now every now and then, and this is the summation over t, I might take some of these entries and delete delta t from that, right? So, but this might not happen every single time because it's only going to happen to the dominant ones. So if I wasn't one of the dominant ones, my frequencies aren't affected, right? Which means that my approximation f prime of I is always greater than or equal to fi minus the sum of all subtractions.
Because occasionally you.
Sometimes you would, so say if you're talking of color red, there is a possibility that red was always subtracted from. But it's possible that yellow in that case was not subtracted from the frequencies, right? So you either participated in all subtractions or maybe some less than that. And that's why f prime I is greater than or equal to fi minus all the subtraction. This is all the subtractions at all time. Fine? Is it clear? So now let's consider this expression, which is the total approximate frequencies, right? So the total frequencies are going to be greater than 0. That is easy. The total approximate frequencies is sum over all the items. So this is I, not T. So understand the difference between the summations. So this is going to be the summation over all the approximate frequencies, which is now less than or equal to what? At every time point, right? So time here is each of these items showing up. I had one item show up at every time point, right? I have one new item at every given time. Minus L over 2, that's the number of entries, so this is like an I entry. Delta T, that's how much I reduced, right? At each time point, a maximum of L over 2 delta T was subtracted.
Yeah, okay. Because half of them will be.
So this is, if this is L, I'm subtracting from L over 2 delta T. That's the amount I'm subtracting.
We're separating from the remaining also, right? Where are you taking only L over 2?
Because
so delta T I'm reducing from all the frequencies, right? Which
this,
is present on
this is the minimum. This is comparing to f prime of I, all the ones that existed out here. This is the minimum that I am at least subtracting. So it's an upper bound. This term is greater than this. You might be subtracting more here, but that is going to be subtracted from f prime of I anyway. This is the amount, this is an inequality. This is not an equality. So this is greater than that, right?
Can you explain what is the intuition behind this?
The intuition is you're trying to figure out what is the absolute upper bound for this value. That's what you're saying. See, the thing is that you're not going to work with equalities here because depending on what the local distribution of my values was, I'm subtracting different amounts. So the question is, what is the absolute minimum that I am subtracting? So if I have some set of counters here, right? Yes, I pick the median, and then that is delta T, correct? I'm subtracting. So if these were my summation of my frequencies, the only part that I'm sure of that I can subtract all the time is this. And this is L over 2 delta T. I might subtract more here, but I'm not guaranteed and I can't give a number here. So I cannot say that it's L times delta T because this is going to depend really on what the counters are looking like. Yes?
Does the distribution have to be, are you assuming a certain distribution?
No, I'm not assuming anything. This is just by the definition of the operation that I'm doing.
Right.
So anybody out here, at least L over 2 entries are greater than delta T, which means that I can subtract. Here there is a flooring going on. I'm not keeping negative values.
I'm talking about the original.
No, there's no assumption. This is just is this clear? Why? So why we are doing this? Because, yeah? So now this summation can be written in terms of n. This is just summation of over T of 1. This is all the entries, right? All the points that you're seeing. You've got n samples.
I got n samples.
N items overall, right?
Okay.
This was sum over all time points. I'm getting one entry every time. And then sum over delta T, L over 2 is what I'm reducing from that. Correct? These are my...
Summation is for both, and delta T sometimes
Yes.
could be zeros, right?
It could be. You're not subtracting it every time. So we're just doing the... So that becomes n. This is the total number of entries that came in. This is L over 2. summation over all times delta t. This is the number of items that you reduced. Okay? And the equalities between these two, the inequalities still exist. Right? Rearranging this, basically this and the 0 out here, because we know that summation over f prime of I has to be positive, you can bring this out and say that the total number of subtractions that you did, right, is less than 2n over L. It's just rearranging this. Understand this because the matrix, the proof for the matrix sketch is going to depend, it's going to look very similar. It's going to be a matrix version of the same thing. Okay? And here, if you set L equal to 2 over epsilon, you're going to get this expression. Okay? And this is the motivation basically, and you will see this, the same structure show up there as well. Is this clear?
Why is the last equation the sum of the last equation?
This?
Yes.
It's this. So I take this is greater than or equal to 0, then I just move it around. It's basically, I started off from here and moved here, and then I just equated this to this, or compared this to 0. Is it clear?
But summation of delta t is not the summation of all the approximation and Trunami. It's approximations at different time steps.
This
So
is
there's
the
still
delta t is the number of items that you reduce your frequencies by at any given time point.
If then you should put 1 by 2, right? But you put L by 2 there. 1 minus L by 2 is.
Yeah, it's L by 2.
So you're assuming if L is 10 and delta t is 3,
Yeah.
then
Delta
you have.
T is not the number of items.
No.
It's the counter.
So okay, let's look at it again.
You're saying L is.
So what is this? What am I saying here? That's the first part. What is it? What am I saying here? That the total frequencies that I'm left off with the end, they are positive, right?
Yes.
There are no negative numbers here, correct?
Yes.
So I'm not dealing with it. I'm only counting stuff. I'm reducing some stuff. If it is less than 0, I'm making it 0. That's all. So this is clear.
Yeah.
I'm maintaining L approximate counters, right? I'm going to end up with some values in there. Those values are f prime of I. I is going to go from 1 to L. Yes? This is what I'm left out with, correct? These are, huh? No, not this. Not this.
No, this is the number of items.
F is, these are the counters, these are frequencies. Frequencies for the item. I'll switch. That's the only confusion here.
Isn't L smaller than T?
L is much smaller than T.
So it's T.
This is L.
No, it's T. Because
Because you're trying to approximate
because
T with L.
You're
it's D, because for sum of f prime is going to be 0. It's D.
That's L.
It's D.
So anything which is not here, so you depends on how. Don't think from a code perspective. Think from a.
That's from theory. It's D.
No theory. It's L. You're only maintaining L counters.
Yeah, but you don't know which one.
Okay, fine. Here, good. D where you will assume some of them are 0. Fine.
Yes.
Okay. So this is
Because they're
good.
approximate. That's the
Sure.
problem.
Okay. Go ahead. It's fine. So either way, this is going over the number of items that you have, not the total number of items, the class of items that you have, and their frequencies, right? Now let's try to write the total number of, so basically an approximation for f prime of I by saying that let's see what we visit, right? So let's visit over all time points, right? So I'm getting values. At every time I'm getting one new item. That is 1, right? So I'm getting one new item. On some time instances, I'm going to, if I'm full of, I've got no empty columns left, I'm going to reduce the entries. I'm going to reduce by delta t.
So is delta t the median at that point?
Yes, that's the definition.
Okay.
We don't know what the median is because this is going to depend on the distribution. So I'm going to reduce by that, and by this argument that I made, the total number that the upper bound on what you're going to reduce it by, the lower bound on what you're going to reduce it by, is going to be L by 2 times delta T, right? So this is greater than or equal to, yeah? Is this step clear? That is this part. I'm just in the last step evaluating this. Sum over T equal to 1 to n, right? So this is going to end up, the first term is going to sum up to n. This is going to sum up to L over 2, sum over T equal to 1 to n delta T. Correct? Yeah? Rearranging this guy is basically, right? So now, if I move this around, I'll get delta T is less than or equal to, right? 2n over L. Right? That's it. Is this clear? What is sum over T delta T? What is that?
Sum of all the medians.
No, the other way to do. That's the amount I subtracted by. That's how much my frequencies here differed from the true frequencies. Yes, that's how much the error is. The total error is how much I reduced it by.
You're not saving the median.
Sorry? I'm not saving anything. This is just a proof. This is just a proof which is giving me how much can my frequencies, the estimated frequencies, vary from the real
So
frequency.
it's still not clear why you are making different.
Can I give an example on the model?
Go ahead.
I think my question is here, like, if I have a distribution, like this, and it's like say T is equal to 45, and I have 10, my L is equal to 10,
Yeah.
and my delta T is equal to 45 is 3.
Okay.
So at that instance, I have 5 elements at least, assuming they are in sorted order, which are more than 3.
Yeah.
So something like this. And then I assume all of them are reversed case just 1.
Yes.
Then at this point I'm subtracting at least this part, right?
Yes.
So which is at this instant I am doing delta T, which is 3 into 5.
Yeah, that's L over 2.
15.
Yes.
So I lost 15 elements in this time step.
Yes.
So but at that point of time delta T is equal to 3. If I do summation of delta 3, I actually lost 15 elements here, but I am not counting the exact loss here, right? My loss is more than 3. My loss should be L 3 into something.
Yeah, total, but this is the, for a given frequency, right? It's f of I. So,
Okay.
I mean, the total,
Can I ask something?
Yes.
Are you sure there's not a typo?
for what?
I think there's something wrong with this one.
Which formula? This formula?
This makes sense. Why is minus there?
Where?
Minus.
Minus where? Here?
No, out there.
Where? Here?
Yeah.
Because you're reducing this.
That should be
Why would it not be minus? What should it be?
If you just think about it, right? If you just think about the number, if you say that then
Look here, right?
many times delta T is 0. That is the reason that formula.
No, you cannot take it seriously.
No. What is your question? I don't understand your question.
My question, I'm just asking, are you sure there's minus?
No, of course there is a minus. Why are you looking there? Try to tell me why you think it should not be minus.
So if we set delta t to the smallest value, which is 1, right, for this case.
Delta T, you don't know what delta T is. Delta T is the reduction. So T is going from 1 to n. Delta T on many time instances, if this was sufficiently large, delta T would be 0 in most of these time instances because you are not subtracting. As long as I have empty slots, delta T is 0. It's only when all my slots get filled that it is there. So every L over 2, I'm creating new L over 2 slots. So it's not really changing. Maybe it's more than that, but worst case scenario, I get new items every time, I fill up L over 2, and then I have to readjust my thing. So it's not, in most, it's as long as L is sufficiently large, it's mostly 0.
And suddenly it will just subtract some elements and then
it will again empty out L over 2. So again for the next L over 2, you have L over 2 slots. So you're filling them, and ideally if the other ones were more frequent, you're going to be accumulating there. So it might actually be more than L over 2 that go past before.
I might have very few delta T's which are non-zero.
Yes. Does everybody get this?
So,
Yes.
Last statement, that is a summation of delta T is less
Yes.
than 2n by L.
Yes.
So, can I translate it in a way like the
You have to
total
use-
error?
Yes. That's here, right? So what is delta T? So let's say you're just talking of one particular item, say red, right? So I kept counting, right? So I kept adding it, I kept adding them. But this is the maximum amount that I might have underestimated, because that's the maximum amount I could have subtracted from my counter. Yes? So that gives me the bound on what is the level of error in my approximation, because this is the same as this, right?
So he's combining equation 2 and equation 3. If you see the equation 2,
Yeah, this one.
he has that sigma. Then now you substitute it and then put
You get it here. Right? Is this clear? Yeah?
I think the problem is because delta T doesn't get reduced from the total number of frequency every time. Like every time you are not encountering non-empty slots.
Yes.
So that's why
No, delta T in those cases is 0.
delta T is actually always the median, but doesn't mean it is you need to subtract to clear
Yes.
out L minus 2
Exactly.
places.
So when you do not have to clear out, delta T is just 0.
Yeah. So having the same substitute everywhere. Either you do delta T or you don't. Basically there are two options. You
So I
subtract
think the confusion is different. Delta T is the amount I'm subtracting at every given time step. In many cases it's 0. If it is not, if they are full, otherwise it's
It's
median.
median, right.
It's not the median always.
It's not the median.
Otherwise, it looks like every
Subtracting the median.
exactly every time.
No, you're not. So delta T is
So
the amount.
delta T is over L over 2, you just subtract L.
You're not subtracting every single time step. I think that at least that part, these guys seem to have that confusion. Delta T is how much you subtract at every time instant, but it's 0 most of the time. Most of the time you're not subtracting anything from the frequencies.
Is there any assumption on the distribution?
No. Did you see any assumption?
No, I just thought for this approximation you will argue that it was.
No, so we never made any assumptions on anything here, right? All we are saying is that something comes in and we subtract some entries from it every time. We are not, actually this is a very relaxed one. In practice, this is going to be much better than this, at least as long as the data is well distributed. This is sort of a really bad approximation in that sense, right? This is just a bound.
Like a theoretical problem.
Yeah, this is just the absolute worst case. So this is what you can guarantee. But in practice, it's going to be much smaller than this.
So it will perform worse with different distributions.
Not than this.
Sorry.
Not
than this, right? But in practice.
In practice, yes, you can. But that's still a pretty good bound. So if you have really good distribution and your data is coming fairly regularly, what are you going to expect? The most frequent guys are coming, so your approximation for the most frequent ones is going to be very good. They're going to stay. So try to now think of what is the worst case. So if you're trying to measure frequencies, forget in terms of whether you got this, forget the error. What is the worst that could happen? That you have one item which always shows up as the last column. So he shows up and he keeps getting chopped off. So you're going to get 0 for him in the end. Whereas if they all came together, he's going to potentially have an entry there which is non-zero. So that's the level of error, and that's what is being characterized by this one out here. Because that's, what is L? L is sort of showing you the history, right? In some sense, the length of the history that you're maintaining. And so you can have those situations where it is, and that's sort of the downside. So if you have those kind of distributions where they are popping up towards the end, it'll get always truncated. Yes?
I don't understand what you by error and setting that.
So this is just allows us to give this bound. This is just instead of representing L as, so this is more of a reworking of this. I'm saying that I have 2n over L. Let me write it as some error, some percentage of n. That is the error. So typically, when you have an approximation algorithm, you want to present it as a percentage of the size of your input. Saying that if I have 1,000 elements and I choose L like this, then 2 over L equal to epsilon is the percentage of error that I can anticipate or expect. The worst case. Yeah. So this is, there's nothing magical going on here. This is just rewriting this expression so that I get it in this epsilon times n format. That's all. Yeah. And if you remember, this is how the other expression looked, right? Where we replaced n by a norm. In this case, we are getting a count, which is ones coming up. So that's why it's n here. Yes, exactly. So there we had a norm for the matrix norm there, and then you had the difference between each of the columns because we are getting a column approximation for the matrix.
So if it was actually n, then you can say that L is too high, basically.
So what you would do is that you can, by doing this, say that we are limited by memory, right? So you can look at it both ways. If you are limited by memory and say that this is the largest L that I can support, that this is the absolute bound on what is the maximum error that I will get with this sort of an approximation, right? The other way to look at it is that if you know that I want at most a 10% error, then you can compute what is the size of error. So that's how it is basically. This really depends on that, and that's all you're doing. Okay, so it allows you to say that if I'm going for an approximation, to get an idea of where it is so that you can interpret your results accordingly, right? So let's think in terms of extending this to the matrix form, okay? I'm going to go over the method first. So this is going to look, for the most part, very similar to what we were doing with these counters. We'll look at the proof later, okay? So do you want to think in terms of, so the first slide is already here. So the difference is that we are maintaining L columns now, okay? So assume that the original matrix was n by d, and we are saying that we are maintaining, because we can't store all of that, we're maintaining only L columns of this matrix. Is it clear? So it's going to go the same way. So the first part is fine. I maintain L, right? So the sketch or the approximation has at most L columns. And we still maintain this property that some columns are empty, right? So these columns are empty. Basically, they're zeros right now. So it's not a sparse matrix, really. It's a special matrix. It's really, in essence, you're estimating a dense matrix. It's just that it's the same as those counters. They're just empty. I'm keeping them zero valued. In this case, empty means zero. So that as I get in a new column, I can put it in, right? The notion of counting is a little bit different here, and the notion of subtracting the median is different. But fundamentally, it's going to be the same operations, right? So as we go over each of these steps, try to understand what you did in the frequent item case when you were counting. Counting should be relatively easy to understand, right? So conceptually, you understand that, and try to make a link to this. If you thought that we had avoided SVD, we are going to go back to SVD at some point. So you have these columns, okay? So this is just an example. I had some column coming in. Now let's say that we got another column of this. So the matrix exists somewhere. It's either coming in from some source or we are reading it from this, and we are reading one column at a time, okay? So we take this column. If there is an empty column out here, we insert it there, okay? So in this case, this whole column will just end up being here.
But the column is actually...
It's a column of A. It's a full column, yes.
But you're having only till D, right?
No, so the original matrix is n by d.
Oh, originally n by D. Okay.
So it's n by d, and I'm maintaining L by d approximation, right? So we are reducing dimensionality in one of
On
them.
one side, okay.
And you can think of it that many cases, that's what it is. One of your side
One of them
is significantly larger than the other. Okay? It's a very hard problem if you want to reduce both.
both sides. Yeah.
So, and there's not that much work there. I do some stuff to actually take care of those situations, which is, it's hard. The approximations are much worse.
Much
there.
complex.
So, we are only maintaining L out here. The columns are still there, okay? Now, at some point, as you insert these, yes? Yeah. Okay. So in this case, at some point, once your matrix gets full, right? So we need to now do the same operation as what we did in the frequent item case when we were counting. So here we have some matrix data, and we want to subtract the median, right? So what is this? So we covered this in many of our classes. So what would be the correct way of doing this? You have the total amount of information. We want to shrink it by half, let's say.
So half of the eigenvalues.
Fundamentally, yes. Is it clear why? Okay. Let's see if the next line. What is the SVD? So you're decomposing your matrix, right, into the sort of a two orthonormal bases. They're orthonormal, and then you have a scaling factor, the eigenvalues, right? They are an indication of the intensity. So these are an indication of the counts, right? When we talk about reducing the dimensionality, it's basically saying we are setting some of them equal to 0, which is that those components which are contributing the least become 0. We need to now take the same value and scale the top items. So in this particular case, what we do is that we decompose it into U sigma and V transpose. The V transpose can be ignored. Okay? There are two ways to look at it. One would be in terms of the covariance, of course, that if we did BB transpose, the V transpose V will be identity because they are orthonormal and they would go away. So they are equivalent exactly in the covariance norm. But even otherwise, if you remember from an SVD perspective, what was U sigma? U sigma was the projection or the coordinates onto your orthonormal basis. That's what it was, and that's what we are doing. So you can take this and you can compute this new orthonormal version, right? Actually, sorry, not orthonormal, orthogonal version in this case, because you've scaled it by sigma, so it's no longer orthonormal, it's just orthogonal. These columns are orthogonal to each other, right? And now we can actually discard some of these if required. Right? Because when I had data coming in as columns, it's sort of, you don't know the underlying basis for that data. So before I can do it, I need to reorient it and make sure that I lose only the least important part. Right? So this is there, this is the same, I already talked about that, right? So the fact that you should do is that once we do an SVD and we compute this U sigma, right? These are now orthogonal to each other, each column is orthogonal, and their magnitudes are decreasing because they have been, each of these columns has been scaled by the eigenvalues which are in decreasing order. That's the magnitude of these orthonormal vectors, right?
They're automatically decreasing.
Correct? Delta in this case is going to be basically this column, right?
Yeah.
That's what it is. This is what you're going to be decreasing it by, right? Now you don't need to go here to decrease. What you're going to do is that before you compute this itself, you will scale the eigenvalues and compute the corresponding scaled version of B. But once this is done, you can just subtract it. You reduce the column norms by delta, right?
So wait, I draw the last two columns and then subtract the first two columns by the middle column, right?
You're not really doing it at the column level, but yes, in principle.
No, in theory that is.
Yes, in principle, you're computing the median value. In this case, it's the fifth. And then I subtract everybody from that. Of course, if you had, I don't want negative eigenvalues here. So if it was negative, I just make it 0. And that's all there is. So I'm scaling these eigenvalues, which are above the median, by the.
Scaling them down.
Yes, so. And now you have empty columns again, and you can iterate, right? So we can start adding more.
But we should multiply the V transpose back, right?
No, you don't need it because it's the projection onto the space. That's all.
But the columns that are coming in are not in the same projection, right?
It doesn't matter. You don't need to do that. I've just reduced it, right?
I understood the reducing
Yes.
part, but I have not understood how you can throw away the V U sigma V, because the ones which are coming has the bias of V, right?
Sure. When you do it again, you're going to get rid of it. It's going to happen.
Or because I'm always throwing it away, no point.
Yeah. So you'll always get that. And this is sort of, for those of you who want to see it, this is the pseudo code of the code itself. So it's very simple. You start off with a 0 matrix, right? So B is initialized to 0. And you start inserting columns one by one. At any point that B is full, basically, that means it has no, it's not full in itself. You have no zero valued columns. You will compute the SVD of B, right? So you do this decomposition. Delta is basically just going to be sigma square L over 2. So it's the middle, the central square of the central eigenvalue. Scale your sigma by that. This is basically subtracting in the L2 sense that value from all eigenvalues. Of course, I don't want negative, so I'm putting in a max here. Compute the new B matrix and repeat. Okay? So the V transpose is, what is it doing? So you have some data, right? The first mapping, so when we decompose the overall matrix, think in terms of what you're doing. So the mapping is the first one is a rotation. This is the orientation. Basically, you're reinterpreting the same data in an orthonormal basis. It is equal. So when we do U sigma, this is the data itself is equivalent. The points that we had, the samples that we had in this orthonormal are equivalent to the original one. It's just that because we were both looking at the data from beginning to end, this V transpose is taking it back. That's why when you consider the overall matrix A, we need to consider the whole thing together. But in terms of the projection of the part that you have seen onto this orthonormal basis, this is correct. So this is the orthogonal basis and the scaling. So this is the projection onto the orthogonal basis that we had. Now if you think in terms of, the other way to look at it is that if you compare in the covariance norm, when we look at V transpose, what is this going to look like? U sigma V transpose, right? And V sigma transpose, which is the same, U transpose. So this is identity now, right? So this goes away. So in this norm, it's exactly the same, right? So this part cancels out, right? Yeah.
Is V also orthonormal basis?
It is. They're both orthonormal.
So
They're just, it's,
only a projection.
yes. So if you remember what we had this discussion last time as well.
Yeah,
on the range, and the V is really doing the opposite. It's the null space
Yeah.
that is being mapped.
What's kind of confusing is because you're adding columns which are not taken off V. The column which you're adding now after we do the
Yes.
U sigma.
That's because we are maintaining this. If for some reason you wanted to go back from this space to the original space, then you would need it. So it's a different thing. Data is always moving in this direction. You're going from A into this
Into the
orthogonal basis out here.
okay.
You're never mapping it back, and that's why we can sort of ignore it. And that's why the covariance where you never go to this, you only temporarily go to this intermediate space, doesn't need to exist. That's why the V cancel out. That's where it stays there, right? So this part, this, which is the column that was brought in from A minus the part that was subtracted in the previous time. So this is our intermediate state that we had before we did the SVD. So at some point, this is what you were saying, that you have a combination of your orthonormal basis things that you removed plus the columns of A that you brought in. That is, we are tentatively representing as C out here. That's all, right? If you compare this with the frequent items case, you'll see that they're almost the same version of the proof, except that you're using the matrix versions of all operations out here. Okay? We are almost up for time, but right, we did this. So just a quick summary, we saw that in the covariance sense, it's summation over all the reductions that we did, and this is less than 2 Frobenius norm of the matrix by L. And again, setting L equal to 2 over epsilon gives us this expression, which is almost exactly the same as the previous one. There is one final thing I want to say. This is a fairly easy concept beyond this, that if you think in terms of parallelism now, you don't necessarily have to do it in a streaming sense anymore. So you can do this in a divide and conquer way, which is that load in some columns, compute a sketch. So let's say we have matrix A as being divided up into 2 stacked versions where you have rows stacked as A1 and A2. You can independently compute the sketch of A1 and the sketch of A2 as B1 and B2. You can stack those 2 sketches together and compute the sketch of that. And of course, you can do this in a recursive fashion. Yes. So instead of think of it in a sense that what are we doing? So even though I said that you're bringing in a column at a time, you're going to bring in L columns at a time, do the SVD, scale it down, get L by 2 again, and do it, right? Now, you can alternately say that I'm looking at blocks of L, compute them all independently as sketches, and start combining the sketches. So the proof for proving that it is actually also has the same bound is there in the paper, and it's very similar to the other proof that we just did. So it's nice because you can do it in the streaming fashion. So if you are doing it on a single machine, reading it from a file one by one, then you're more likely to do it one at a time. Whereas if you were to do it in, say, Hadoop or something, you're going to distribute it, right? Or MPI for that matter, where everybody can load as much as they can, compute the sketch, and then start combining sketches, right? And so both versions exist for this. So again, understand the basic algorithm is very simple. You're just bringing in columns at a time till it gets full, compute the approximation, make up some space, start bringing in more data, and keep updating this. That's all you're doing. The approximation error, if you did have the true approximation, is basically going to converge as well. So potentially, so when we thought about the randomized SVD case, we talked about a case where even though we're doing projections, so in some sense we are looking at all data, we are only getting K projections, right? So one way of looking at it is that we're not looking at all the data out there. You're getting a K-dimensional look at your data. You need to still access the data that way. Here, again, you could stop this the way you're building your sketch before you have seen all of the matrix. The more you see of it, the closer you're going to get to your error as well, right? So that is the other aspect of this. Is this clear? No, so you will have to, it's going to converge much more slowly. So it's not, you can start looking at proofs of how many columns you would have to get an approximation. I'm just saying that you can potentially get a good enough approximation before you have looked at every single column.
So the approximation that you get is because of treatment enough need to certain items.
In this case, or
Treat.
in this case, it's the same idea as with the frequent items, that if you're looking at the most dominant characteristics or the most frequent items, you are getting the most maximum information in from your sketch. You're not getting everything, so you are losing information, but hopefully what you're losing is the part of your data which doesn't vary as much. So it has a very small component overall.
This is slightly better than standardized.
To slightly better than
To the
Randomized compared.
no, compared to what? They are very different. So depending on what your situation is that you are going to look at these, they're somewhat different approaches to the same problem. You would rarely apply, you might not have the choice of applying both for the same problem. Like I said, the difference is that randomized SVD operates with the whole matrix, but is reducing the total amount of work you're doing. Here you are looking at all the data, right? But you have a constraint that I cannot load all the data at once. So the requirements are a little bit different. So if I did not have an issue of storage, if I could load it, if I could compute my projections, so a lot of the problems that I deal with, I never have the matrix. I only can compute the projection. So in which case this method is not really viable. The cost of me generating the matrix is 1,000,000 times greater than doing any such computation. So that situation never arises. But if you could, and if you had the full flexibility, I would go for a randomized SVD with something larger than K for a K-rank approximation. That's going to give me a better bound. These are very different situations. Like I said, they're solving a similar problem, but the assumptions under which they're solving it are very different. So you need to understand where to use what.